We've talked a little bit about the domains of log functions as we were graphing them. And in general, the rule is just this. The argument, which is the thing you're plugging into log, that's the thing when you rewrite it in exponential form, it becomes the result, okay? The argument must be strictly positive, okay? That's because if I have the log base b of, I'm just going to write a for the argument, is equal to, oh, let's just say c, okay? When I rewrite that in exponential form, this is saying it's the exponent I need when b is the base. To get a, that's the argument, that exponent is c. Okay. But that's saying that the argument is the result of taking this positive number b to a power. And I know if I take a positive number to any power, it's going to be positive. Okay, so I want to just practice getting some domains. So let's say that f of x is the log of x plus 5. So of course, by not writing a base here, I'm saying that it's the common log. What the base is, though, does not matter, because the base is always going to be a positive number other than 1, and so the rule is always the same. Okay, the argument must be positive. Okay. So I can sort of understand this one graphically, because I know that adding 5 before we plug into the log is actually just shifting things 5 units to the left. But I would just solve this algebraically. X plus 5 has to be bigger than 0, so x has to be bigger than negative 5. Okay. If I were to graph that on a number line, it looks like so. And so my domain is everything from negative 5 to infinity. Okay. Now, in that particular case, it's easy to understand the domain in terms of the graph of the function. But if I have a more complicated argument, I might want to rely a little bit more on the algebra. Let's suppose that g of x is the natural log of x squared minus 4. Now, that's not just a simple transformation of the types that we've studied. This is still a function composition. I'm plugging the polynomial x squared minus 4 into the log function, but the compositions that lead to our transformations are those that just involve arithmetic operations, adding or subtracting a number, or multiplying or dividing by a number. Okay. But I can still find the domain. I can simply say this means that x squared minus 4, that's the argument, has to be strictly bigger than 0. Now that's a polynomial inequality. So I want to remember how I solve those. What's nice is because I'm setting it bigger than 0, that's the first step anyway. I want to be comparing to 0 so that I can think in terms of the signs of things. And then I want to get the left side factored. Well, that's a difference of 2 squares. So I can say x plus 2 times x minus 2 has to be bigger than 0. Then I find my boundary points. My boundary points would be the things that would make this equal 0. So that would be a negative 2 and a 2. And with log functions, it's always going to be a strict inequality, so I don't want to include those boundary points. And then I can just check. So I'm going to just record below the number line, x plus 2, x minus 2. I'll record the signs of those, and I'll record the overall sign above the number line. So if I pick a test number, let's say I pick negative 3. Negative 3 plus 2 would be negative. Negative 3 minus 2 would be negative. 2 negatives would multiply to give me a positive. Okay. Between negative 2 and 2, I could pick 0. 0 plus 2 is positive. 0 minus 2 is negative. A positive times a negative would be negative. And to the right of 2, I could pick 3. 3 plus 2 is positive. 3 minus 2 is positive. And 2 positives will multiply to give me a positive. I was looking for where this thing was positive, so I want this interval here and this interval here. So my domain would be everything from negative infinity to negative 2, union 2 to infinity, with parentheses around both the negative 2 and the positive 2. Okay. Notice with this inequality, you might have been tempted to move that 4 over and say x squared has to be bigger than 4. Not helpful, okay? Because I could take the square root of both sides, but this would give me the absolute value of x. I could actually do that. I could say the square root of x squared has to be bigger than the square root of 4. So the absolute value of x has to be bigger than 2. Okay, but I don't just get x has to be bigger than 2. I get the absolute value of x would have to be bigger than 2. I think it's simpler to just factor this. If I were doing this, I could say, okay, let's look at our boundary points. My boundary points would be the 2 points whose absolute value is equal to 2, and then I could just pick some test numbers. Okay. So it is possible to do it that way, but it's not as simple as you might have thought, because remember, the square root of x squared is not x. It is the absolute value of x. All right, so let's take a look at another example. Let's suppose I had h of x equals the natural log of x squared plus 4. Okay. Now, I kept g of x up because these are very similar looking, but they're actually very, very different. In both cases, the rule is the same. The argument has to be bigger than 0. So x squared plus 4 has to be bigger than 0. Well, it is, okay? Because the smallest that x squared could be would be 0. I'm adding 4 to that. That's going to make this strictly positive. So this is always true. Now, you might be able to see that by inspection, and if you do, great. Okay. So my domain is everything from negative infinity to infinity. Don't forget to answer the question and actually give the domain. Okay. If you didn't notice this right off the bat, you could try factoring this and it wouldn't work. Okay. You could try the quadratic formula. A is 1, B is 0, and C is 4. Okay. So the things that would make this equal to 0 would be if x is equal to the opposite of b would be 0, plus or minus the square root of b squared is 0 squared, minus 4 times 1 times 4 all over 2a. That's plus or minus the square root of negative 16 over 2. Now, when we're talking about these functions, we are working in the real numbers. Working with just polynomials, we sometimes work in the complex numbers. We have not defined how to work with exponential and log functions in the complex numbers. It can be done, but that's an upper division class. Okay, so we are working in just the real numbers, so there's no solution. Now, that doesn't tell me that the domain is all real numbers. That tells me the domain is one of two things: everything or nothing. Because what that tells me is that this is either always positive or always negative. It never changes sign. Okay, so now I could say, okay, here's my number line. There are no boundary points. Let's pick a test number. Let's just pick 0. If I plug in 0, oh, it's positive, so it's always positive. So my domain is that. Okay. You could also rearrange that to say x squared has to be bigger than negative 4. Sometimes that's a little bit easier to see. I know a perfect square is always bigger than any negative number. So that's another way that you might see that this is something that's always true. Although in general, remember, if you've got a polynomial, you're going to want to keep things on the left side so that you can factor. All right, so I'm going to have you folks try one. So this is one from the homework so that you can pause the video, work out this problem, and you are getting a head start on the homework. This is number 89 from the homework. I want you to find the domain of p of x, which is the log of x squared minus x minus 12. So find me that domain in interval notation, and we'll start the next video going over that together.